Ashanti was commissioned in 1961. The German Navy launched the first coal-class frigate in 1961 with two Brown, Bovary and C gas turbines in the world's first combined diesel and gas propulsion system. The Soviet Navy commissioned in 1962 the first of 25 Kashin-class destroyer with 4 gas turbines in combined gas and gas propulsion system. Those vessels used 4 M8E gas turbines, which generated 54,00072,000 kilowatt, 72,00096,000 HP. Those ships were the first large ships in the world to be powered solely by gas turbines. The Danish Navy had 6 Southern-class torpedo boats, the export version of the British Brave-class fast patrol boat, in service from 1965 to 1990, which had 3 Bristol Proteus, later our Proteus, marine gas turbines rated at 9,510 kilowatts, 12,750 shp, combined, plus 2 General Motors diesel engines, rated at 340 kilowatts, 460 shp, for better fuel economy at slower speeds. And they also produced 10 Wilhelmus-class torpedo forward/guided missile boats, in service from 1974 to 2000, which had 3 Rolls-Royce Marine Proteus gas turbines also rated at 9,510 kilowatts, 12,750 shp, same as the Southern-class boats, and 2 General Motors diesel engines, rated at 600 kilowatts, 800 shp, also for improved fuel economy at slow speeds. The Swedish Navy produced 6 Spica-class torpedo boats between 1966 and 1967 powered by 3 Bristol Siddeley Proteus 1282 turbines, each delivering 3,210 kilowatts, 4,300 shp. They were later joined by 12 upgraded Nyköping-class ships, still with the same engines. With their aft torpedo tubes replaced by anti-shipping missiles, they served as missile boats until the last was retired in 2005. The Finnish Navy commissioned 2 Turunmaa-class corvettes, Turunmaa and Karjala, in 1968. They were equipped with one 16,410 kilowatts, 22,000 shp, Rolls-Royce Olympus TM1 gas turbine and 3 Wärtsilä marine diesels for slower speeds. They were the fastest vessels in the Finnish Navy. They regularly achieved speeds of 35 knots, and 37.3 knots during sea trials. The Turunmaas were decommissioned in 2002. Karjala is today a museum ship in Turku, and Turunmaa serves as a floating machine shop and training ship for Satakunta Polytechnical College. The next series of major naval vessels were the 4 Canadian Iroquois-class helicopter-carrying destroyers first commissioned in 1972. They used 2-foot-4 main propulsion engines, 2-feet-12 cruise engines and 3 Solar Saturn 750 kilowatts generators. The first U.S. gas turbine-powered ship was the U.S. Coast Guard's Point Thatcher, a cutter commissioned in 1961 that was powered by 2 750 kilowatts, 1,000 shp, turbines utilizing controllable pitch propellers. The larger Hamilton-class high-endurance cutters was the first class of larger cutters to utilize gas turbines, the first of which, Ussig Hamilton, was commissioned in 1967. Since then, they have powered the U.S. Navy's Oliver Hazard Perry-class frigates, Spruance and Ali Burke-class destroyers, and Ticonderoga-class guided missile cruisers. USS Markin Island, a modified Wasp-class amphibious assault ship, is to be the Navy's first amphibious assault ship powered by gas turbines. The marine gas turbine operates in a more corrosive atmosphere due to the presence of sea salt in air and fuel and use of cheaper fuels. Civilian maritime, edit. Up to the late 1940s, much of the progress on marine gas turbines all over the world took place in design offices and engine builders' workshops, and development work was led by the British Royal Navy and other navies. While interest in the gas turbine for marine purposes, both naval and mercantile, continued to increase, the lack of availability of the results of operating experience on early gas turbine projects limited the number of new ventures on seagoing commercial vessels being embarked upon. In 1951, the diesel-electric oil tanker ORI's, 12,290 deadweight tonnage, DWT, was used to obtain operating experience with a main propulsion gas turbine under service conditions at sea, and so became the first ocean-going merchant ship to be powered by a gas turbine. Built by Hawthorne Leslie at Hebburn-on-Tyne, UK, in accordance with plans and specifications drawn up by the Anglo-Saxon Petroleum Company and launched on the UK's Princess Elizabeth's 21st birthday in 1947. The ship was designed with an engine room layout that would allow for the experimental use of heavy fuel in one of its high-speed engines, as well as the future substitution of one of its diesel engines by a gas turbine. The ORI's operated commercially as a tanker for 3.5 years with a diesel-electric propulsion unit as originally commissioned, but in 1951 one of its four 824 kilowatts, 1,105 bhp, diesel engines, which were known as Faith, Hope, Charity and Prudence, was replaced by the world's first marine gas turbine engine, a 890 kilowatts, 1,200 bhp, open-cycle gas turbo alternator built by British Thomson Houston Company in Rugby. Following successful sea trials off the Northumbrian coast, the ORI's set sail from Hebburn-on-Tyne in October 1951 bound for Port Arthur in the US and then Curaçao in the southern Caribbean, returning to Avonmouth after 44 days at sea, successfully completing her historic transatlantic crossing. During this time at sea, the gas turbine burned diesel fuel and operated without an involuntary stop or mechanical difficulty of any kind. She subsequently visited Swansea, Hull, Rotterdam, Oslo and Southampton, covering a total of 13,211 nautical miles. The ORI's then had all of its power plants replaced with a 3,910 kilowatts, 5,250 shp, directly coupled gas turbine to become the first civilian ship to operate solely on gas turbine power. Despite the success of this early experimental voyage, the gas turbine did not replace the diesel engine as the propulsion plant for large merchant ships. At constant cruising speeds, the diesel engine simply had no peer in the vital area of fuel economy. The gas turbine did have more success in Royal Navy ships and the other naval fleets of the world, where sudden and rapid changes of speed are required by warships in action. The United States Maritime Commission were looking for options to update World War II Liberty ships, and heavy-duty gas turbines were one of those selected. In 1956 the John Sargent was lengthened and equipped with a General Electric 4,900 kilowatts, 6,600 shp, HD gas turbine with exhaust gas regeneration, reduction gearing and a variable pitch propeller. It operated for 9,700 hours using residual fuel, bunker C, for 7,000 hours. Fuel efficiency was on a par with steam propulsion at 0.318 kg/kilowatt, 0.523 pound/HP per hour, and power output was higher than expected at 5,603 kilowatts, 7,514 shp, due to the ambient temperature of the North Sea route being lower than the design temperature of the gas turbine. This gave the ship a speed capability of 18 knots, up from 11 knots with the original power plant, and well in excess of the 15-knot targeted. The ship made its first transatlantic crossing with an average speed of 16.8 knots, in spite of some rough weather along the way. Suitable bunker C fuel was only available at limited ports because the quality of the fuel was of a critical nature. The fuel oil also had to be treated on board to reduce contaminants, and this was a labor-intensive process that was not suitable for automation at the time. Ultimately, the variable pitch propeller, which was of a new and untested design, ended the trial, as 3 consecutive annual inspections revealed stress cracking. This did not reflect poorly on the marine propulsion gas turbine concept though, and the trial was a success overall. The success of this trial opened the way for more development by GE on the use of HD gas turbines for marine use with heavy fuels. The John Sargent was scrapped in 1972 at Portsmouth Pa. Boeing launched its first passenger-carrying waterjet-propelled hydrofoil Boeing 929 in April 1974. Those ships were powered by 2 Allison 501 kF gas turbines. Between 1971 and 1981, Sea Train Lines operated a scheduled container service between ports on the eastern seaboard of the United States and ports in northwest Europe across the North Atlantic with 4 container ships of 26,000 tons DWT. Those ships were powered by twin Pratt & Whitney gas turbines of the Foot 4 series. The 4 ships in the class were named Euroliner, Eurofreighter, Asia-Liner and Asia-Freighter. Following the dramatic organization of the petroleum exporting countries, OPEC, price increases of the mid-1970s, operations were constrained by rising fuel costs. Some modification of the engine systems on those ships was undertaken to permit the burning of a lower grade of fuel, i.e., marine diesel. Reduction of fuel costs was successful using a different untested fuel in a marine gas turbine, but maintenance costs increased with the fuel change. After 1981 the ships were sold and refitted with what at the time was more economical diesel-fueled engines, but the increased engine size reduced cargo space. The first passenger ferry to use a gas turbine was the GTS Finjet, built in 1977 and powered by 2 Pratt & Whitney Foot 4C1DLF turbines, generating 55,000 kilowatts, 74,000 shp, and propelling the ship to a speed of 31 knots. However, the Finjet also illustrated the shortcomings of gas turbine propulsion in commercial craft, as high fuel prices made operating her unprofitable. After 4 years of service, additional diesel engines were installed on the ship to reduce running costs during the off-season. The Finjet was also the first ship with a combined diesel-electric and gas propulsion. Another example of commercial use of gas turbines in a passenger ship is Stena Line's HSS-class fast-craft ferries. HSS 1500 class Stena Explorer, Stena Voyager and Stena Discovery vessels use combined gas and gas setups of twin GELM 2500 plus GELM 1600 power for a total of 68,000 kilowatts, 91,000 shp. The slightly smaller HSS 900 class Stena Charisma uses twin ABB Still GT35 turbines rated at 34,000 kilowatts, 46,000 shp, gross. The Stena Discovery was withdrawn from service in 2007, another victim of too high fuel costs. In July 2000 the Millennium became the first cruise ship to be powered by both gas and steam turbines. The ship featured 2 General Electric LM 2500 gas turbine generators whose exhaust heat was used to operate a steam turbine generator in a coax, combined gas electric and steam, configuration. Propulsion was provided by two electrically driven Rolls-Royce Mermaid azimuth pods. The liner RMS Queen Mary 2 uses a combined diesel and gas configuration. In marine racing applications, the 2010 C5000 Mystic catamaran Miss Geico uses two Lycoming T55 turbines for its power system. Advances in technology, edit. Gas turbine technology has steadily advanced since its inception and continues to evolve. Development is actively producing both smaller gas turbines and more powerful and efficient engines. Aiding in these advances are computer-based design, specifically computational fluid dynamics and finite element analysis, and the development of advanced materials, base materials with superior high temperature strength, for example, single crystal superalloys that exhibit yield strength anomaly, or thermal barrier coatings that protect the structural material from ever higher temperatures. These advances allow higher compression ratios and turbine inlet temperatures, more efficient combustion and better cooling of engine parts. Computational fluid dynamics, CFD, has contributed to substantial improvements in the performance and efficiency of gas turbine engine components through enhanced understanding of the complex viscous flow and heat transfer phenomena involved. For this reason, CFD is one of the key computational tools used in design and development of gas turbine engines. The simple cycle efficiencies of early gas turbines were practically doubled by incorporating intercooling, regeneration, or recuperation, and reheating. These improvements, of course, come at the expense of increased initial and operation costs, and they cannot be justified unless the decrease in fuel costs offsets the increase in other costs. The relatively low fuel prices, the general desire in the industry to minimize installation costs, and the tremendous increase in the simple cycle efficiency to about 40% left little desire for opting for these modifications. On the emissions side, the challenge is to increase turbine inlet temperatures while at the same time reducing peak flame temperature in order to achieve lower NOx emissions and meet the latest emission regulations. In May 2011, Mitsubishi Heavy Industries achieved a turbine inlet temperature of 1,600 degrees Celsius, 2,900 degrees Fahrenheit, on a 320 megawatt gas turbine, and 460 MW in gas turbine combined cycle power generation applications in which gross thermal efficiency exceeds 60%. Compliant foil bearings were commercially introduced to gas turbines in the 1990s. These can withstand over 100,000 start-forward/stop cycles and have eliminated the need for an oil system. The application of microelectronics and power switching technology have enabled the development of commercially viable electricity generation by microturbines for distribution and vehicle propulsion. In 2013, General Electric started the development of the GE9X with a compression ratio of 61:1. Advantages and disadvantages, edit. This section contains a pro and con list. Please help rewriting it into consolidated sections based on topics. June 2022. The following are advantages and disadvantages of gas turbine engines. Advantages include 1. Very high power-to-weight ratio compared to reciprocating engines. 2. Smaller than most reciprocating engines of the same power rating. 3. Smooth rotation of the main shaft produces far less vibration than a reciprocating engine. 4. Fewer moving parts than reciprocating engines results in lower maintenance cost and higher reliability /availability over its service life. 5. Greater reliability, particularly in applications where sustained high power output is required. 6. Waste heat is dissipated almost entirely in the exhaust. This results in a high-temperature exhaust stream that is very usable for boiling water in a combined cycle, or for cogeneration. 7. Lower peak combustion pressures than reciprocating engines in general. 8. High shaft speeds in smaller free turbine units, although larger gas turbines employed in power generation operate at synchronous speeds. 9. Low lubricating oil cost and consumption. 10. Can run on a wide variety of fuels. 11. Very low toxic emissions of CO and HC due to excess air, complete combustion and no quench of the flame on cold surfaces. Disadvantages include: 1. Core engine costs can be high due to use of exotic materials. 2. Less efficient than reciprocating engines at idle speed. 3. Longer startup than reciprocating engines. 4. Less responsive to changes in power demand compared with reciprocating engines. 5. Characteristic whine can be hard to suppress. Major manufacturers, edit. 1. Siemens Energy. 2. Ansaldo. 3. Mitsubishi Heavy Industries. 4. Rolls-Royce. 5. General Electric. 6. Silmarsh. 7. ODK. 8. Pratt & Whitney. 9. P&W Canada. 10. Solar turbines. 11. Alstom. 12. Zuriamash Proect. 13. MTU Aero engines. 14. MAN Turbo. 15. IHI Corporation. 16. Kawasaki Heavy Industries. 17. HAL. 18. PEL. 19. Magna. 20. Techwin. 21. Doosan Heavy. 22. Shanghai Electric. 23. Harbin Electric. 24. AECC. Testing, edit. British, German, other national and international test codes are used to standardize the procedures and definitions used to test gas turbines. Selection of the test code to be used is an agreement between the purchaser and the manufacturer, and has some significance to the design of the turbine and associated systems. In the United States, ASM has produced several performance test codes on gas turbines. This includes ASM PTC 22-2014. These ASM performance test codes have gained international recognition and acceptance for testing gas turbines. The single most important and differentiating characteristic of ASM performance test codes, including PTC 22, is that the test uncertainty of the measurement indicates the quality of the test and is not to be used as a commercial tolerance. See also, edit. 1. List of aircraft engines. 2. Centrifugal compressor. 3. Gas turbine modular helium reactor. 4. Pneumatic motor. 5. Pulse J. 6. Steam turbine. 7. Turbine engine failure. 8. Wind turbine. References, edit. 1. Rag.